Hello, today we are going to do section 4.5, which is about verifying inverses using composition of functions. So essentially what we're going to be doing is combining section 4.3 and 4.4 today. In 4.3 we first learned what it means to compose functions or do composition, and in 4.4 we figured out how to do an inverse. We're going to put it together today. So, you know that for any function f, each x value corresponds to exactly one y value. That's the definition of a function. So for a one-to-one function, one x value to one y value, it is also true that each y value in the range corresponds to exactly one x value in the domain. So not only is it one x to one y, but one y to one x. So you can only have one going in each direction, if you kind of think of it visually. So a one-to-one function, f, has an inverse. Remember that we write our inverse notation as f with a little -1 exponent. This is also going to be a function. So if f goes from a to b, then f must also go b to a for f inverse. So functions are considered inverse functions. We have this cool rule here that we can say that two functions, f and g, are inverses if you compose them. So if I do f composed with g, and I get x back, and then I do g composed with f, and I also get x back. So remember, the composition notation has that little open circle in it. And when we compose functions, what you're doing is you're taking the second function and plugging it into the first function in the notation here. So on this one, g is going to plug into f, and we should get just x back when we do that. And on this notation here, f is going to plug into g, and when we do that, we should just get x back. And if we do, we would say that both f and g are inverses. So it's just a way to check to see if two functions are inverses by doing that composition. So let's practice a couple. So here we have this function g of x is equal to 4 over x plus 2. And then they're asking each of these following questions. So for part A, they just want us to find the inverse of g. So remember last time we learned to do the inverse. Essentially what you're doing is you're switching your x with your y. And you can think of g of x as being your y. So I'm going to switch these two places so that I get x equals 4 over y plus 2. And then we work backwards to solve for y. We want to get y alone. On this one, it's kind of unique because right now y is in the denominator, which we do not like. So in order to get y alone, first I have to get it out of the denominator. So we're going to have to kind of make this messier before it gets better. So what we're going to do is we're going to think of this binomial here, this group, and we're going to times it by itself. Because if I times a fraction by its denominator, these are going to cancel with each other, but then I also need to multiply the other side as well. So those cancel and we're left with just a 4 over here. Like I said, we're going to have to make this messier before it gets better. But we're going to now distribute that x through so that I get y times x plus 2x. Okay, and then now what we're going to do, again, we're still trying to get y alone. I know it looks kind of messy. We're going to minus this 2x over to this side so that these cancel. And I have y times x equals 4 minus 2x. And now, to get y by itself, I need to get rid of this x. So right now they're being multiplied, so the opposite would be to divide by x. So those cancel, and we get y, which remember, y is essentially g of x. So here, since I switched my g to y, I'm now going to switch it back to the g notation, but because it's the inverse, I'm going to put that little -1 on it. So we're saying the inverse of g is equal to 4 minus 2x over x, and that would be our inverse. Okay, so a little review on finding inverses there. Now what it's saying to do on part B is we're going to do the composition of g composed with g inverse of 0. So remember, when we have this notation here, especially when we have a number inside instead of an x, you're going to work backwards to the front. So first what we're going to do is we're going to take 0 and we're going to plug it into our inverse function. So I'm going to do G inverse with 0 plugged in. So if I do that, I get 4 minus 2 times 0 over 0. But that's a problem, right? We're not allowed to divide by 0. So this one we would say does not exist. There's an error there. We're not allowed to divide by 0. But let's try the other direction. Now we have G inverse composed with G. So these are different. Notice the order of the G's in the inverse. This time G comes second. So we're plugging 0 into G first. So if I plug G of 0, I'm going to put a 0 into my G function. We're going to have 4 over 0 plus 2. And this is okay because we have this plus 2 here. So I'm not dividing by 0 anymore. 0 plus 2 is just 2, so I get 4 over 2, which is 2. You guys can't see my paper. So once we get this answer, we plug that into G. Now we're plugging 2 into our inverse. So I'm going to take 2 and plug it into the inverse of G. So we're going to take 2 and plug it into here. So I'm going to have 4 minus 2x, but instead of x, we're plugging 2 in, over x, which is 2. And then we're going to simplify. Well, 2 times 2 is 4. 4 minus 4 is 0. 0 divided by 2 is just 0. So that would be our answer. So remember, the order matters on our compositions. A composition in one direction might not work out, but if I flip the direction, it might. So we can't say that these are going to be equal to each other because most of the time they are not equal to each other. So now we're just going to practice verifying that two functions are inverses using that composition rule. So remember that rule states that if we have two functions, they're going to be inverses if I compose them and get x back in both directions. So I need to do the inverse composed with f and get x back. Then I need to do f composed with the inverse and get x back. You do have to check both ways. I know it can get kind of redundant and annoying to check both of them, but that's how this rule works. So we need to verify, again, we're verifying here, we're showing that it works by doing both of these. So to verify that two functions, f and g, are inverses of each other, we need to show g composed with f, you just get x back, and f composed with g, you just get x back. So remember, g composed with f, that means we're plugging f into g. You can also write it this way, g of f of x. Think of plugging f into your g function. And then f of g means you're plugging g into f, or you can write it this way, g of x plugged into f of x. So you're working from the backwards to the front, or think of it this way, you're working from the inside out. So let's practice verifying. So remember, you're going to show both. I need to do g composed with f of x, and I need to do f composed with g of x. It doesn't matter which one you do first, but you do need to show both. So if I do g composed with f, that means I'm taking f and plugging it into my g function. Well, my f function is 3x minus 2. I'm taking this entire equation and I'm plugging it into the x in my g function. So instead of x right here, I'm plugging this entire thing. So I'm going to plug in 3x minus 2 plus 2 over 3. So I plugged this entire thing into my g function. You don't necessarily need the parentheses here, but if that kind of visually helps you to see that you've put the entire f function into the entire g function, go ahead and do it. So now we plugged them in. The way we cancel these numbers is important. You can't just start canceling all crazy. You need to think of your order of operations. So here I have 3x minus 2 plus 2 over 3. The correct way for canceling here is we would need to do anything in the numerator before we can cancel top to bottom. So first we would say the negative 2 and the plus 2 cancel with each other. So that would give us now 3x over 3. And now that the 2's are gone, I can cancel the 3's with each other and I just get x back, which is what we're looking for. So far, so good. Now let's try the other direction. We're going to take g and plug it into f. So this entire fraction x plus 2 over 3 is now going to plug into the x in the g function. So I'm going to take this equation, but instead of x, I'm putting this whole fraction in. So we're going to have 3, and then instead of x, I'm typing in this whole x plus 2 over 3 fraction, and then we have that minus 2 on the back. So again, this whole thing is just getting replaced by the g function. And again, when we start canceling, I need to do the order. So when you guys are doing your homework, you have to have the steps correct. You can't just start canceling in any order. So on this one, the 2's canceled first, but actually on this one, this 2 I can't cancel while it's being multiplied by the 3. So this times by 3 will cancel with the divide by 3, and I have left over x plus 2 minus 2. And I know we get lazy and we don't want to show this middle step, but I do need to show this middle step. Now I can cancel the 2's, and I have just the x back. So since this composition ended with an x, and this composition resulted with an x, we've done this proof right here. We've verified. So we can say that f and g are inverses. Okay, that's what we're practicing today. So we're pretty much just verifying that they are inverses of each other. Okay, let's try another one. For sake of time, I think we'll skip this middle one. Let's go down to the number 3. So we want to verify that this function and this function are inverses of each other. So again, you need to show both directions. I'm going to do g composed with f of x, and I also need to do f composed with g of x. So the order matters here. The second equation is going to get plugged into the first equation. So I'm plugging f into the x right here. So here's my equation that I'm replacing the x with. So I'll have parenthesis, but instead of x, I'm plugging this entire thing in. It's kind of long, but we can do it. So we're going to have the square root of x plus 10. Notice that the 10 is under the square root, but the minus 6 is not. So that's just the x, but then I had this plus 6 here. And then it's being squared minus 10. So this part right here, this is your f. We've plugged this f function into the entire g function. So now we're going to start canceling, but again, the order matters on how you cancel, and you need to write all the steps out, even though we're kind of lazy and it gets annoying and we don't want to do it. So on this one, the things that would cancel first are going to be inside the parentheses. We can cancel this minus 6 and this plus 6. So then our next step, and we do need to write this part down, is we're left with the square root of x plus 10 inside the parentheses being squared, and then we have the minus 10 on the outside. So right now I can't cancel the 10's while I have this square root and this square. But luckily, this square cancels with the square root, and now the x plus 10 can come out, and I have the x plus 10 and then the minus 10. Now the 10's can cancel, and we get just the x back that we need. So we're good there. So now let's check the other direction. So we're going to do g composed into f. So g is going to plug into f. So this entire thing is going to plug into the x inside that square root. So when these get really long like this, it's really easy to leave off a piece. So make sure you write everything down. So I'm taking this whole thing and it's going to plug into the x in the square root. So I need a really long square root, because instead of x, I'm plugging this entire thing in. So I'll have x plus 6 squared minus 10. That's just for this x though. Don't forget this little plus 10 now goes on the back. I wrote that a little longer than I need to. And then we have this minus 6 behind the square root. So again, order matters. The first thing that I can cancel here, I can't cancel the 6's yet because I have too much stuff going on. The square root can't cancel with the square while I have these 10's here. So the 10's are going to cancel with each other first. So that leaves the square root of x plus 6 squared, and then we have that minus 6. So again, I can't cancel the 6's while that square root's there, so the next step would be to show that the square and the square root cancel. And that leaves us with x plus 6 minus 6. And I know it's annoying to write that last step down, but you need it. So now the 6's cancel, and we get the x back. And so we're good. So we would say that f and g are inverses. So I mean, essentially what you're doing here is you're doing a proof. And in math, proofs are very, very particular. You have to show every little step in order to actually prove something. So I know it gets kind of annoying to write all of these little steps down, but you have to do it in order to show that it's proved or proven. So that is how that will work. Again, I know it's redundant, but you have to go through those little steps. You'll also get a couple questions with tables and graphs, but again, I think these are the easier versions. If you're given a table and they want you to find the inverse, remember, inverse is you just flip your x and y. So if this is x and this is f of x, this is now going to be f inverse. So just make sure you get your notation right. We need that little -1. But the x column is now going to be my inverse y column. So I'm going to switch the columns, -7, -6, -5, all the way down. And then the original y column is now going to be my x column. So it's pretty straightforward. You could literally teach a 5-year-old how to do this. 1 and 4. So the x column goes to the y column goes to the x column. So tables are nice and easy. And then for graphs, what you're going to do is try and find points. This one kind of bolded points for you, but you're going to try and find where they're going right through like a little intersection on the graph, and you're just going to flip the x and y coordinates. So what that means is if we look at this point, actually let's do this point first. This point is over 2 and up 5. So if my original point is at 2, 5, let's say this is f of x, my inverse point is going to flip. It's going to be at 5, 2. So I'm just going to do that for these 3 points that I have bolded on here. This one is at 1, 1, which when you switch it just stays 1, 1. But then this one is over back 1 and then down 2. So it's at -1, -2. So that's going to flip to -2, -1. So once you have the new points, you're just going to go graph those. So let's go over, kind of off the graph, over 5 up 2. We'd have a point right here about, if we just kind of extend that graph. And then we have one at 1, 1 again, so it just overlaps. And then -2, -1. And then here's the tricky part, because I am just a human and not a computer. We're going to try and connect these points so that it looks right. And remember, these should kind of be a mirror image of each other. They should be reflecting over this line y equals x. So kind of think of this shape as flipping over, and that will do that. When you guys do it on the computer though, it's a little bit easier because the computer will draw a nice pretty graph for you. You don't have to do it by hand. So let's do one more on this one. So just find your 3 points. On this one we're back 1 and up 4. So -1, 4. So the new point for the inverse will be at 4, -1. This second point is over 1, up 5. So the new point will be at 5, 1. And then this one is over 7, up 6. So the new point will be 6, 7. So then you just go and plot those. We're going to go over 4, down 1. Over 5, up 1, and then over 6, up 7. And then we're going to just connect our dots, and I am so bad at doing that and making it look good. So something like that. Again, on the computer, it will do it nice and pretty for you. But you should see kind of that reflection, how it reflects across that diagonal line. So there's graphs and there are the tables. I think those are the easier ones. And then just a reminder, when you are doing the composition of inverses, you're doing essentially a proof. So you have to show every little step, proving that from here you get x. And if you do this, you get x. And you need those middle steps in order to essentially prove it. But if you guys have any questions, as always, please don't hesitate to reach out. I love talking to you guys and helping you. So send me an email and we can do a Zoom call and answer your questions. Hope you guys are staying safe and healthy, and I will talk to you later. See ya.